Something happened last week. I don't know why the recording didn't work. It didn't post, but hopefully it'll work this week. So this week we are moving on to the next step, and that is hypothesis testing. And what hypothesis testing is, it's a way of making decisions, but it's a very, very specific process. And so the hypothesis testing process, one, you make an assumption about a population parameter. Now, for this class, we're only going to be doing population means and population proportions, but it could be a standard deviation or a variance or a range or other population characteristic, proportion, or parameter that we would want to make decisions about. Typically, that assumption is not what we're trying to prove. That assumption in many cases is the opposite of what we're trying to show or what's in our own interest. That assumption is typically a current standard, or most of the time it's a safe claim. Like if we're doing medical testing or drug testing, it would be the old treatment. The assumption would be that the old treatment is the best treatment. And then we try to gather evidence around that. Second, then after we make that assumption, we gather a sample and calculate statistics from the sample. And then finally, we decide if the results of the sample are consistent with what we would expect from if the assumption we made was true. So now we don't expect it to exactly agree with our assumption. We just expect it to not completely disagree with it. It can disagree with the assumption a little bit, and we can write that off to random variation. It's if it's way away from what we assumed, then we would have to say, well, there most likely really is a difference, so that the assumption is probably wrong. The key note here is we are not gathering evidence to prove the assumption. We are only gathering evidence in an attempt to, I shouldn't say disprove it either, because we don't technically completely disprove it, but in an attempt to show it is unlikely. So let's take a look at how this process works. Because of this idea that we are only gathering evidence, we're not gathering evidence to prove it, we cannot, and I put that in capital letters, we cannot ever prove the assumption correct. So never say we accept the assumption. Or we have proven, or anything like that. There are only two logical conclusions or two acceptable conclusions, and we'll get to those in just a few minutes here. So the assumption that we make is called the null hypothesis. And the abbreviation for it is H with a subscript 0. Now, from now on, I'm just going to write H with a 0 after it instead of trying to do it in subscript, just for sake of speed here. But that null assumption can take on one of three forms. So the first, that null hypothesis might be that the mean I'm just going to use U instead of mu. I don't have a mu key. Remember, the mean is technically the Greek letter mu, is equal to some hypothesized value. If that is the case, then the alternative hypothesis would be, and of course we label that H1 since the null is H0. Some textbooks label it HA for alternative, would be that the mean is not equal to the hypothesized value. This is what we call a two-tailed test. What does that mean? Well, that means is this null hypothesis, the hypothesized value, that assumption is used to create a sampling distribution, hypothetical sampling distribution. Since we're claiming that it's exactly equal to the value, well, then we could disprove, well, not disprove it, but it would show that it's unlikely if we get evidence, if we get a sample value that's way too large, or if we get one that's way too small. Equals means right down the middle. So it could be, it's called a two-tailed test because we can reject the null hypothesis if we get evidence far enough out on either tail. The second form of the null hypothesis is that the mean is less than, I should say less than or equal to. It's always the or equal to always goes with the null hypothesis. Hypothesized value. Now, then the alternative would be H1, is that the mean has to be the opposite, greater than the hypothesized value. And this is what we would call a one-tailed, right-tailed, or upper-tailed test. Because what that means is, in our hypothetical sampling distribution in the bell curve, since we're saying that we're less than or equal to a certain value, the only way we could contradict that is if we got a value in our sample that is far enough on the upper end, large enough. So right-tailed or upper-tailed section of that distribution. The third form of the null hypothesis is that the mean is greater than or equal to a hypothesized value. And in that case, the alternative would be that the mean is less than that hypothesized value. And again, this is what we would refer to as again, it's a one-tailed test, but it would be a left tail or lower tail test. So again, we're looking at that sampling distribution, that bell curve. And here we would, since we're saying that the assumption is that the mean is greater than or equal to a given value, we will reject that assumption if we get a sample result that's far enough down on the lower tail or the left tail of that distribution. Now, the tricky part here is the wording for the null hypothesis is almost always, I'm depending on the textbook, but this textbook, I believe, always words it as that the mean is equal to a value. The reason it does that is because we're using that null hypothesis to create this hypothetical, one of these hypothetical sampling distributions. So equals establishes the center of that distribution. The mean would be right in the middle. So then we have to rely on the alternative hypothesis to decipher what we really mean by that, that null hypothesis. So if the alternative is that the mean is less than a value, we know then that the null hypothesis really was saying that the mean is greater than or equal to that value. They just used the equal notation to establish that sampling distribution. So then there are two processes. Both of them will give, if done correctly, the exact same answer, exact same conclusion to a test. But the first process is what we call a critical value approach. So in the critical value method, first step is we use the alpha value. I'm just going to write out the word alpha instead of trying to remember it's the Greek A, or the little fish. Alpha and the alternative hypothesis to determine the critical value of Z or T for the test. Then we create a rejection rule from this critical value and the alternative hypothesis. And then we gather the data, calculate a test statistic from the data. Should say from the sample data. And then finally, make the decision, draw the conclusion. Does our sample result fit with our assumption that we made? Or the second one is something called a p-value method. In the p-value method, we still find the test statistic from the sample data, but then we calculate the probability of a more unusual result. This is again based off of H1 as to what direction would be unusual. And then we compare to alpha. Well, let's show you what I mean here. So the test statistic for a mean is just a z-score. So z is equal to some sample value, x bar, minus the mu, the population mean. In this case, it would be the hypothesized mean from the null hypothesis, divided by the standard error. So that's sigma, the population standard deviation, divided by the square root of the sample size, n. So let's look at an example of this. Let's see, the average age of a college freshman nationwide is 22.8 years old. With standard deviation of 1.7 years. A sample of 45 Franklin University students. Gives a mean age of 22.1 years old. Test the claim that Franklin's freshmen are the same age as the national average at alpha equals 0.05. Okay, I see someone in the chat here. Let me check that out. Okay, so this test statistic will be totally different from a probability. The probability actually comes into the p-value. So let's take a peek here. First, first step, of course, is to set our hypotheses. Our hypothesis, the null hypothesis here is exactly what they're saying, that the freshmen are the same age. So that the mean age of the freshmen at Franklin University is 22.8. The alternative then is that they are not 22.8. So this is a two-tailed test. Now we need to find our critical value for our test statistic. And we'll do this from our bell curve. Since it's two-tailed, alpha is the probability in the tails. Since it's two-tailed, that 0.05 gets split between the two tails, so it's 0.025 on each tail. Next, we need to know if this is a z-test. Can we use the normal distribution? And yes, it is a z-test because up here, we are given the population standard deviation of 1.7 years. This is the average age of college freshmen nationwide. That is our whole population. So we have the population standard deviation, so we can use a z statistic here, a z-test. So let's find our critical value of z. So second, distribution, inverse normal, 0.025, giving us a mean of 0, standard deviation of 1, of course, for standard normal, giving us a negative 1.96. If we do the same thing for the 0.975, which is the upper end, we should get the same value, just positive. And we do, positive 1.960. So our critical value here, this one is a negative 1.960. And this end up here is a positive 1.960. So what this does is allows us to create our rejection rules. We'll reject if we're over in this area or if we're over in this area. So for the critical value method, we will reject the null hypothesis if the test statistic is less than a negative 1.960 or greater than a positive 1.960. So let's calculate our test statistic. This is a z statistic since we're using a z-test. We have our sample mean of 22.1 minus our population mean of 22.8 over that population standard deviation of 1.7 years divided by the square root of that sample size of 45. So let's find this test statistic. So 22.1 minus 22.8. So we get a negative 0.7 years, and this is going to be divided by, now in parentheses here, I put my standard deviation of 1.7 divided by the square root of my sample size of 45. Make sure I get out of there and close my parentheses. And I get a negative 2.762 as my test statistic. Well, this, since the test statistic, of negative 2.762 is less than the critical value of negative 1.960, we will reject the null hypothesis. So that is saying there is sufficient evidence to reject the idea that Franklin students are the same age as the national average. I should say Franklin's freshman students rather than just students. Now notice I didn't say that they were younger than the national average because that's not the alternative hypothesis. The alternative hypothesis is just that they're not equal to the 22.8. It doesn't say less than or greater than, just not equal to. So in our conclusion, we cannot specify a direction because the alternative hypothesis did not specify a direction. It just said we're far enough away from it on one side or the other. Now the second side of this, or the second possible method, would be to do a p-value method. We'd still have to create our hypotheses, but with alpha of 0.05, the rejection rule is, for the p-value method, And it's always less than for the p-value method. We will reject the null hypothesis if the p-value is less than alpha of 0.05. So how do we find the p-value? Well, the p-value is the probability of being further away from the center than we are, and then multiplied by the number of tails. So I'll give you an example of what I mean there. So that's our test statistic of a negative 2.762. So let's do a normal CDF of being less than that. So from negative infinity to negative 2.762 with a mean of 0 and standard deviation of 1. With that probability, now that's only on one tail. Since this is a two-tailed test, we do have to multiply by 2. We get 0.0057. Now this is approximate because we rounded our test statistic. So a p-value is 0.0057. So since the p-value of 0.0057 is less than alpha of 0.05, we reject the null hypothesis again. So that would lead us to that same conclusion. There is sufficient evidence to reject the idea that Franklin's freshmen are the same age as the national average. Well, that's not a terrible amount of work, but the calculator can make life a lot easier for us. So let's go to the calculator here, and rather than just doing p-values and probabilities, let's do the whole test. So a stat test. This is a z-test. We are using our sample statistics. Our hypothesized mean in the null hypothesis was 22.8. The population standard deviation was 1.7. The sample mean was 22.1. The sample size was 45. And next we want the alternative hypothesis. Since the null hypothesis was equal to, the alternative has to be not equal to. So that's that first option there. Then we hit calculate. And there we get the negative 2.762 and the p-value of 0.0057, which is approximately what we got. We were a little different because of rounding. So there's the exact conclusion we got. Calculator spits it out in a few seconds. So this was a z-test because we had that population standard deviation. What if we don't have the population standard deviation? Well, just like with confidence intervals, we would do a t-distribution test. So our test statistic just uses, instead of a population standard deviation, it uses a sample standard deviation. And of course, we use the t-distribution. So our example is the university claims that students complete their degrees in less than 5 years. A random sample of 62 graduates gives a mean time to complete of 5.12 years with standard deviation of, I want to go 0.78 years. Now it's a little subtle here, but you can see that that is a sample standard deviation because it was the sample that gave the 0.78 years, not accepted standard or nationwide or whatever. We're going to test the claim at alpha equals, let's do 0.05 again. So let's do our hypotheses. The null hypothesis is the university's claim that the mean is less than 5 years. So usually we'll just typically write it as the mean equals 5 years, even though we know that it really is the mean is less than or equal to 5 years. The alternative then will be that the mean is greater than 5 years. So this is a t-test and it is one-tailed. And it's on the right tail or upper tail. So we're looking at being somewhere up in here. That alpha of 0.05 is all right there. But now we can't just do an inverse normal because this is a t-test. It's important that we know that the sample size is 62 because remember, when we do the t-distribution, we have to have degrees of freedom. So let's go to the calculator here. We're going to do second distribution, inverse t. Our area, now this is always the area to the left. So we've got 0.05, but that's on the right tail, so it'd be 0.95 to the left. Degrees of freedom, so sample size of 62. Degrees of freedom is always one less than the sample size. That's 61. Now we paste it in. And we get 1.670 is our critical value. So that means is our critical value rejection rule would be, oh, come on. There you go. We reject the null hypothesis if the test statistic is greater than t critical of 1.670. And then, of course, the p-value rejection rule, it never changes. We will reject HO if the p-value is less than alpha. In this case, again, alpha is 0.05. So let's find that test statistic. I'm going to go right to the calculator here. So we're going to go stat over to test, and this is a t-test. So we are going with the summary statistics again. Our hypothesized value of the mean is 5 years. Our sample value is 5.12 years. Sample standard deviation is 0.78 years. Sample size was 62. The alternative hypothesis is greater than, so we select greater than that value, and then calculate. So we get T of 1.21, p-value of 0.115. So test statistic, T equals 1.21, p-value equals 0.1152. Well, our conclusion for the critical value, since the test statistic of 1.21 is not greater than the critical value of 1.670, we fail to reject the null hypothesis. Or if we're looking at the p-value, again, since the p-value of 0.1152 is not less than alpha of 0.05, we fail to reject the null hypothesis. So these conclusions will always be the same, whether you use critical value or p-value. They're just two different ways of going about it. So then the overall conclusion here would be that there is not sufficient evidence to refute the university's claim. So we can't say that they're wrong. Now we notice we did not prove their claim. We failed to reject their claim. We did not accept it. We just failed to gather enough evidence against it. So be very careful with your wording on those conclusions. So now our final type of test is for proportion. And as we've seen with our confidence intervals and everything, the proportion works slightly different. Our test statistic for proportion will always be a z statistic. And it's going to be, again, p hat minus p, which is the population value, or in this case, the hypothesized value in the null hypothesis, over the square root of p times 1 minus p over n. Now, since we don't actually have the value of P, we use the sample value, the P hat in there for P, unless we have another estimate, but usually we do not. So let's look at our example here. So let's say that the bookstore claims that a majority of students now use ebooks instead of hard copy textbooks. The random sample of 400 students gives that 218 use hard copy. In other words, 182 use ebooks. Test the bookstore's claim. Add alpha equals, let's go 0.90. So our null hypothesis, H0. Bookstore claimed a majority of students. So is that the mean is greater than or equal to 0.5, or not the mean, it should be the proportion. P is greater than or equal to 0.5. Now notice I just put equal to, even though we really know it's greater than or equal to 0.5. We only use equal to as our notation to create that hypothetical sampling distribution. So then the alternative is that the proportion is the other direction, less than 0.5. So here's our curve. The alternative is less than, so our alpha of should not have been 0.90, should have been 0.10 for 90%. So all of our alpha of 0.10 is down here on the tail. So we define that critical value. So the calculator, second distribution, inverse normal, 0.1, mean of 0, standard deviation of 1, gives us a negative 1.282. This is a negative 1.282 is that critical value. So again, our critical value rejection rule. We will reject the null hypothesis if the test statistic is less than z critical of negative 1.282. Or the p-value rejection rule. We will reject the null hypothesis if the p-value is less than alpha of 0.10. So let's see what we get here. First of all, this is going to be a test for proportions. So we have to make sure we use the correct function on the calculator. So stat, over to tests again. We have to go down to a one proportion z-test right here. Our hypothesized value of the proportion is 0.0 or 0.5. X here is the number that are successful. Now, 218 use hard copy, but remember, the bookstore was talking about ebooks. So it's the 182 that are using ebooks that we want there, out of a sample size of 200 or 400, I should say. And the alternative is less than. So we select less than there. Then we go to calculate. Now we get z of negative 1.8 and a p-value of 0.0359. So our test statistic z was negative 1.8. The p-value of 0.0359. So we're going to have the same conclusion either way. Critical value conclusion. Since the test statistic is less than z critical of negative 1.282, we will reject the null hypothesis. Or the p-value method, since the p-value is, let's go, the p-value of 0.0359 is less than alpha of 0.10, we will reject the null hypothesis again. So that is saying is there is sufficient evidence to dispute or refute the bookstore's claim. Notice again, we did not disprove their claim, but we gathered sufficient evidence to say that it was unlikely. So we gathered sufficient evidence to refute it, to reject it. There's still a chance that it could be true. So this brings us to a discussion of potential errors in hypothesis testing. So first, there's what we call a type 1 error. A type 1 error can only occur when you reject the null hypothesis. And what it is we reject H0 when it really is true. So there is a chance that we could reject the null hypothesis even though it was true. This will happen when we get an extremely unusual sample. What's the probability of getting that unusual sample? Well, that's equal to alpha. That's what that alpha value is that we are setting, is what chance are we willing to take of rejecting this null hypothesis when it really is true, but just because we get just a really extreme sample. Because what we're saying is when we say an alpha of 0.05, what we're saying is there is a 5% chance that even if the null hypothesis is true, that we can get a sample that's extreme enough that we would still reject it. Well, we say that the chances, since the chances of getting that sample are sufficiently small, we're willing to take that risk. Now, if it's a case where falsely rejecting the null hypothesis could be disastrous, like in medical testing, if we know that the current treatment is working and having some effectiveness, we don't want to reject it and switch over to a new treatment unless we are sure that the new treatment is as good or better than the old one. So that's where we might set alpha at 0.01 or even 0.005 to make very, very sure that it wasn't just a bad sample. Now, the other thing we do to avoid type 1 errors. So the first is choose a smaller value of alpha. The smaller alpha is, the less likely it is to have that type 1 error. But the other thing we do is if we reject HO, we repeat the experiment, the test. If we reject HO again, then it confirms the result. If we fail to reject HO on that second run, well, then we want to do more testing. Now, maybe even rejecting it twice in a row isn't enough. Maybe we want to do the test and reject the null hypothesis 4 or 5 times in a row before we finally decide that we're going to accept that, or not accept, but we're going to reject the old treatment and go over to the new one. This is exactly how medical testing goes. The first test has to show a significant improvement with the new treatment, but then we have to do it again and again. It has to be repeatable over and over again. So that's one of the ways that we limit that possibility of a type 1 error. Next is a type 2 error. We use the Roman numeral 2 with 2 capital I's. And this is failing to reject the null hypothesis when it really is false. So we didn't quite get enough evidence to reject it, but it really isn't true. It really is false. Well, that is really how the type 2 error is very common in hypothesis testing, because the deck is stacked in favor of that null hypothesis. We are not going to reject a null hypothesis unless we have very strong evidence against it. So type 2 errors happen a lot because hypothesis testing is designed to play it safe. We have an accepted value, we stick with it unless there is strong evidence against it. Now, again, you can decrease the chance of a type 2 error by choosing a larger value of alpha, but then you're taking that risk of rejecting the null hypothesis if it really is true. So most of the time we are risking, we're willing to risk a type 2 error because the null hypothesis is already an accepted value, and keeping the null hypothesis does not present much of a risk. Okay, I rambled a little bit at the end there, but that actually is all of the material for this week. I think hypothesis testing is actually easier than confidence intervals, just because we've already kind of used to that idea of sampling distributions and how they affect our confidence intervals. And we're used to using the calculator. Now we're just using the z-test, t-test, and one proportion z-test instead of the z-interval, t-interval, and one proportion z-interval. So it's just different commands, but it's really the same input. So with that, does anybody have any questions? Did that answer your questions, Maddie, as to how the test statistic comes about?
Yes, that helped. Thank you.
You bet.
And when you said that we would repeat the test over again for type 1 errors, do we repeat it the exact same way, or?
Well, that is a little bit beyond the scope of this course. Yes, what it is it's like I said, it's repeatability, and it's not the same researcher repeating it. Usually you're having a different researcher trying to reproduce your test. So based off of your process. So they're looking at your notes, trying to reproduce your experiment and get similar results. And if they don't, that's when you both kind of have to go back to the drawing board. That's most drug companies, when they're doing those tests, they will do the tests themselves, and then they have to go to an independent researcher to confirm their test, and then the FDA approves the next stage of testing.
Okay, so we don't have to do any retesting or
No.
repeating. Okay, perfect.
So in this class, we will perform the test, and that will be it. I was just presenting that as in the real world. That's a very common method of confirming it several times before we put it into practice.
Okay.
Will we get any questions that we'll have to confirm if it is an error of any kind at all, or?
Basically, all that would ask is what type of error is possible. And so if we reject come on, the null hypothesis, then the only possible error is a type 1 error. If we fail to reject the null hypothesis, then the possible error is a type 2 error. And that's really all it's going to ask is what type of error is possible. Well, if you rejected the null hypothesis, you'd say, well, type 1 error is possible here. Or if you failed to reject, you'd say a type 2 error is possible. And they might ask, what would a type 1 error mean to this problem? Well, it would mean that we rejected the null hypothesis even though it was true. So it's just going to be simply asking things like that. It won't ask you what's the probability of the, well, it might ask you what's the probability of a type 1 error, where you just have to answer whatever value alpha was. But it's not going to ask us to calculate the probability of a type 2 error or anything like that.
All right, awesome, thank you.
You bet. If this were a more advanced course, there's something called the power of a hypothesis test, which is the probability of that type 2 error, but it's kind of a complex process. we're not going to put you through that in this basic course. Okay, with that, I will shut the recording off.